Welcome. My name is Tim Calvo. I'm with Hosokawa Micron Powder Systems, and today we're going to discuss a recipe for a perfect lab. 4 key ingredients. We're going to be talking about the Hosokawa Micron Laboratorio pin mill, model LPM. We'll also be talking a little bit about the Hosokawa Micron Labo mixer, LV1. We will also talk about the particle size analyzer, the micro airjet sieve, model MAJSX, and we will also be talking about the powder characteristics tester, model PTX. In order to have a lab that will provide you with the best possible information, the material specifications play a vital role in what pieces of equipment will be needed. So, for example, some of the items that may be of interest will be particle size, others might be the flowability, others might be how well they blend together. So, what we're going to talk about first is size reduction. The size reduction can consist of different methods. However, today we're going to be talking a little bit about attrition as far as the setup of the equipment, as well as impact or hammer milling. Some people reference it as such. When you're dealing with pin mills, they can give you a finer top size to a coarse size, that being anywhere from 35 to 65 micron, and hammer mills, simply because of their nature and how the top size is controlled, that can range anywhere from 75 micron to a coarse side of 750 micron. What we see in this slide is basically a pin mill. A pin mill consists of a rotating disc and a stationary disc. Typically there, the material is fed in through the center, and it requires to pass through the rotating disc gaps. As the material comes in contact with the gaps or contact with the pins as it's trying to pass through the gaps, it causes for size reduction. So as such, you're able to get a finer product. The top size can be controlled by means of the speed of the rotating disc. Now, when you're looking at other forms of grinding, you look at the attrition disc, which is suitable for temperature sensitive material. And then you also have the more coarse grinding, the swing hammers and or rigid rotor. Depending upon what your application requirements are, the disc accordingly will be used. When it comes time for impact milling or hammer milling, you're going to be controlling your top size by the means of a sieve screen. That screen will then be held in place, and the material must be fine enough to pass through those openings in order to become satisfactory or controlled, and that's going to be reliant on the feed rate of the material, the speed of the rotor, and then the actual characteristic of the product. The example you see in front of you is the typical example of what the attrition disc can acquire. So you can see there's various forms of plastics, candidly called, that will have different characteristics in the grinding process. The attrition disc gives you that flexibility of being able to grind a wide variety of different materials, and as you can see, you can also vary the achievable fineness. Other materials such as foods or chemicals, or in some cases here like a phenolic resin, which while it's still a little bit of a kind of a plasticky, you can still grind with the hammer mill or impact mill, And this is an example of the achievable finenesses that would enable you in your lab to produce the product that would be best suited for your application. Common markets, as we here at Hosokawa Micron Powder System look at it as food, pharmaceutical, mineral, chemical, but then there's also those sub-markets that go, connect with those general markets. For example, your sports equipment or your marine technology or aerospace. So it's not just limited to food, pharmaceutical, mineral, chemical, but those are the core application markets that many other markets spin off of. All right, now we'll talk a little bit about low shear mixing. Low shear mixing with the LV1, the Labo mixer, is typically used for free-flowing product, fragile and or heat sensitive, or a combination of both. Low shear, quite frankly, means that there is very low impact on the product, which can potentially cause for degradation of the material. So with the LV1, as you see in this next caption here, that has little effect on the product. The capacity of this particular vessel is a 2.5 liter, that's a water fill, and just a small volume less or percentage less for the actual working area. What's nice about this mixer is that it can reproduce the same mixing effect at 30% of the overall 2.5 liter mixing. So it gives you a good flexibility should you contemplate scale up. Now, free-flowing powders, this is one of the topics that we talk about as far as that this particular mixer is good for. You can see here just in this rendition of, we have black particles and white particles, and then we run it through the mixer and we identify and see how well the mix or the blend has become. A more practical demonstration would be, here we have black balls and red balls, and then we've run the Labo mixer. You can see now with the caption on the right, we have a more homogeneous mix of the two different colors of balls. So as you can see, it's very low shear. There's been no detriment to the product, and just a nice, easy, gentle mixing process. What's nice about this particular model machine is that not only does the screw rotate, but also the vessel rotates. Both the vessel and the screw constructed in stainless steel, so that if you have an application that requires a contamination-free environment, this will give you a very good, let's say, satisfaction to that range. It's also a very compact design. It's approximately 2 foot high, so it fits nicely on a typical lab bench. There is very little deviation in the variation of the mixing. So for example, we have, it's either on or off, we have a speed control, and then we have timing control, which I'll discuss a little bit further. What's also nice about this particular mixer is there's a protective polycarbonate door which allows visibility of the mixing process during the operation, but it also prevents the operator or anyone else from introducing or putting a hand in there or something. It's a safety feature. So from that aspect, you have not only safety, but visibility. As I mentioned a little bit before, simple on-off controls. You've got your push buttons, you have your speed control for your screw, as well as it also affects your bowl just slightly there. It's usually, as you can see here, 2 to 1. And you're decreasing timer controls. This ensures repeatability when you're trying to duplicate a prior application or a prior batch. The other nice feature about the unit, it does not require continuous servicing or lubrication from that aspect. Now let's talk a little bit about particle size analysis. Particle size analysis, when you're looking at a product, truly is dictated by how, let's say, repeatable or what the level of quality of the product is. Because if you have varying particles and you're trying to process a material or some type of additive, you can actually vary the effectiveness and how well that material is going to be used in the end product. Some of those end products may have a sensitivity to their bulk properties or their stability or their appearance, because typically when let's say your particles are much finer, the coloration of the product gets also lighter. So when you're dealing with, let's say, pharmaceutical, your product performance can be varied because the finer the product, depending upon the surface area, can have a direct effect on how, let's say, strong that particular, prescription or product may be. So it's very important to identify the particle size. Now, from the beginning of time, there's always been a need, and it was identified at that time, to have consistency in particles. Most times, like the caption here, is more like there was a hand grinding of wheat so that you could produce the various breads. And then the quality of the breads are dictated by the fineness or the graininess or the grittiness of the breads. There was a very crude but yet effective sieve screen at that time, and this is what enabled for the various qualities of different types of materials, most likely breads. All right. In today's technology, we use the pneumatic sieving process. That process utilizes air to distribute the particles across the top of the screen and to identify the particles that are typically over or under. The pneumatic sieving process was developed in the mid-60s and has proven to be one of the most simple yet most repeatable process. However, during that, there are some points that need to be stressed, which I'll stress a little bit later. What occurs with the pneumatic sieving process is that ambient air is brought in through a duct, which is then directed by means of a rotating slit nozzle. As it rotates beneath the sieve screen, it distributes the particles that are captured between the screen and the sieve cover, because you're working under a negative pressure. All right. As you can see here, this would be the area for which the sample is located. This gives you an indication of how it looks like in the actual machine. The red line depicts where the slit nozzle is located, and as it rotates clockwise, it basically pushes the product around in a circular pattern, allowing for all the particles to come in contact with the sieve cloth or the sieve screen, however you want to call it. Those particles that are fine enough to pass through the cloth are then carried away in the airstream. As they're carried away in the airstream, you get a much more repeatable analysis, but at the same time, you actually dislodge particles that may have become lodged in the screen during the initial process. This is one of the key advantages to this particular method, which enhances the reliability of the process. All right, this is just a clean shot of the actual unit. You can see the discharge hole there in the center of the bowl, the sieve screen, the sieve cover, etc. All right, an optional part of this particular unit is a cyclone. In this case here, we've matched the cyclone to the typical airflow that's used in the instrument, enabling us to achieve a 98-99% separation at 10 micron. Now, keep in mind, it's pneumatic, so you may have some carryover, but it gives you a clear separation of the particles. What's nice about this is if you're looking for a product that is greater than 10 micron, but less than the corresponding sieve screen that is used in the instrument, the cyclone would then be employed and provide you with the fraction that you're looking for. All right, as I mentioned a little bit earlier, we're looking at sample size. Sample size is critical in the process simply because you want repeatability. So we suggest anywhere between 10 to 100 grams. This will all be product dependent because of the density. I mean, let's face it, you have 100 grams of feathers, so you're going to have a much greater volume of feathers, and that may be too great for the actual cavity between the cloth and the sieve cover. However, you want to have that repeatability, so you want to try to stick with the same volume from sample to sample to sample. And the other reason why most people say 10 to 100 grams is that's just simple mathematics, which in the micro airjet sieve is no longer a major concern because of the software that's been developed for this process. The next would be sieving time. So we talked about the sample volume. Now we talk about the sieving time. You want to have a consistent sieving time. If you're going to measure a product, one at 1 minute, one at 6 minutes, you could potentially have a different effect or a clear differential in the sample. So from that standpoint, you want to be consistent with your sieving time. And with today's technology, you have digital timers on it, you're going to be consistent. The next would be vacuum pressure. Vacuum pressure is very important, especially if you're trying to analyze a highly friable or easily fractured particle. You want to have either a lower pressure or a higher pressure. As mentioned before, that pressure of air actually is a negative pressure, and that also affects the jet as you go around beneath the screen, enabling the cleanliness of the screen to take place simultaneously. This particular item being the sieve screen, the integrity. It's clearly evident the screen on the left-hand side should not be used for analysis of whatever type. The Scotch tape is really a no-no. Some people actually use nail polish or some type of a hardening liquid to seal off larger openings. You really need to have a consistent, non-wavy, non-damaged screen to perform your analysis. So the screen on the right is an example of a good, solid, accurate sieve screen. So to recap, your operational parameters to ensure your reliability is going to be the sample size, sieving time, vacuum pressure, and I cannot emphasize enough the integrity of the sieve screen. The sieve screen is the most critical part of particle size analysis, and the integrity of it is equally as important. All right, some of the advantages of the micro airjet sieve, alias known as the MAJSX. It has the built-in electronic timer along with a modulating pressure valve that can control the vacuum pressure during the process, and it maintains the vacuum pressure. Sometimes as the slit nozzle, alias the wand, passes over the discharge, the pressure might vary slightly, but this is all controlled by the modulating valve, which is then controlled by the software. The next advantage is it automatically calculates the percentage, be it passing or retained. So you can quickly identify what your test results, either on screen or via the printed document. This is a typical, let's say, setup of a basic model with a cyclone and then the various types of vacuums. Optionally, you can go to called the advanced model, which enables you then to print and save the data, and that would then utilize a balance. There are specific balances and vacuums that are recommended because they produce the same acceptable, let's say, conditions. The vacuum, be it the air, the balance, be it the communication between the electronics. All right. Some of those important application areas: particle size. Not only is it research and development, it's quality control, both incoming and outgoing. It's just process control. It's just a wide array of different areas that are particularly specific to your applications. Now, some of those applications, as I mentioned before, food, pharmaceutical, mineral, and chemical, they also divert into sub-levels. So you may have, for example, in the aggregate, well, you look at certain characteristics when you're producing a road or materials for roads. Basically, your cements. You want your cements to have a consistent product. In many cases, it is the finer product offers a greater strength. So these are some of the characteristics that you need for your quality control aspects. Also in drug delivery, as I mentioned earlier, drug delivery, you want to make certain that you're getting the proper amount of active drug to the area that's needed. This is all part of your particle size analysis and control. Size, you wouldn't want to be rubbing a stone against your cheek when you're using your, let's say calcium carbonate for your face powders, nor would you want to have an overly gritty material in a cake mix, or for that matter, try to make coffee with whole coffee beans. This is all relative to particle size analysis. All right, now, once we've achieved the particle size, let's now look at how well those powders flow against themselves, or if they're influenced by any other, let's say, effect. The Micron powder characteristics tester has been developed around the Carr indices. Ralph Carr Jr. developed these indices back in the mid-60s to determine how well powders flow or solids flow. Since the development of that particular set of standards, ASTM has looked at it and developed a standard for the characterization of the flow. Now, some of the terms that you might hear when looking at the Carr indices is flowability and floodability. And we'll talk a little bit about that on some of the upcoming screens. Key points that you need to identify prior to performing a characterization or identification of the characteristics of the material is know your particle size analysis. Typically speaking, the finer the particle, the poorer the flow. Why is that? Simply because the flow is controlled by the surface area of the particles. There's potentially a greater level of cohesion with finer particles than there would be with coarse particles. Another influencing factor would be the hygroscopic nature of the product. Does the product absorb moisture just by sitting out open? It would be something that you'd want to have, let's say, awareness of prior to performing the powder characterization. All right, flowability. Quick and simple. Stationary to moving. What will it take to get the powder to go from steady state to a moving state? Does it require a little bit of, let's say, agitation? Does it require a little bit of different angles? Because every powder will have a different angle of repose, which we'll talk about here shortly coming up. Free-flowing particles, you have a small surface area, kind of spherical in shape. They're non-hygroscopic. However, again, those small particles typically have a higher density than a blend of different sizes within. But yet that's also going to be dictated by where the powders will be used. Floodability. Simple. How can you affect, or how does the material become affected by external influences? Flooding can cause for the powder to flush completely through where you want it to be, have a controlled movement state. So if you're trying to fill, for example, a tablet press, number one, you need to know the natural flow rate, or let's say the flow angle of the product. And number two, do I need to control it once it starts flowing? And this is where the floodability tests will prevail and provide you with that additional information. Okay, what constitutes a floodable powder? Pardon me. Uniform size can have an effect. The larger surface area unquestionably will have an effect. Lower density, because now you have the varied particle size in the sample. These all have a direct effect on the floodability of the powder. All right, what tests within the powder characteristics tester identify flowability and floodability? Each of these tests or methods that are used to identify your sample is measured within the powder characteristics tester. Angle of repose just determines basically how well the material is going to flow against itself. The larger the heap, the poorer the flow. Compressibility commonly is because the finer, it's a higher degree of compressibility. Compressibility is a calculation that goes from aerated to packed, etc. Cohesion. Do my particles have a natural attraction to each other, alias cohesion? This identifies the flowability of some of these that I've talked about. Angle of fall. Well, how do I get the angle of fall? I know what the angle of repose is, but now I've stimulated the angle of repose to identify how that heap is going to change. That then is called the angle of fall. Angle of difference, of course, is the calculation. But now I want to see if this material is going to stay intact during transport. So let's identify what the dispersibility is. The dispersibility is we literally drop the sample onto a prepared dish to determine how much of that material disperses. It's a consistent height, and we just a consistent sample, and we can identify that. So we can put a percentage value to the dispersibility. Some of the enhancements of the powder tester, because over the years there have been a wide array of different powder testers, all performing the same tests. However, some of them were completely dependent upon the operator's subjectivity. So that just added an additional variable to the different products from technician to technician. So you may have had the same product, but you may have had different results because of the human factor. So as a result, what we've done is we've incorporated a charge-coupled camera that actually takes a photograph and binarizes the photograph and then takes the measurements from the photograph. This increases the accuracy and it eliminates the concern or the question that the operator may have, giving you a higher degree of repeatability. The shocker. The shocker at one time used to be just a loose weight that we drop onto a stanchion or a platform. That has now been redeveloped, and we have a consistent G-force of weight dropping from the same height time after time. Once again, enhancing the reproducibility of the test or analysis. Angle of spatula. Angled spatula is a method that's used to determine the internal friction of the product. We use the camera here as well, but we've incorporated a heat gauge. This gauge gives the operator the, let's say, the indication of you have sufficient sample, do not overload it, do not, do not underload it. So this, once again, increases the reproducibility. Some of the other enhancements are in the cohesion test. At one time, there was an optical gauge that the operators needed to monitor to be able to set the amplitude of the vibration to 1 millimeter. No longer. This is done by a proximity device, and it's electronically controlled. This, once again, eliminates the operator error and provides the consistency from test to test. Next, the software is extremely user-friendly. It is all menu-driven, so it guides you through the entire process, making it much more simple to use, as well as I keep saying, repeatable. One of the last enhancements of this particular model is the fact that the software has been built to be compatible with Windows-based operating system. It is completely compatible with Windows 10. It was originally designed for Windows 7, so there should be no issue whatsoever in installing the software on a computer of your selection. However, it should have a Windows-based operating system. The other is compliance with the FDA CFR 21 Part 11. This gives you the registries and allows you to be compliant should you need to have that level of, let's say, performance or conformance. The next is it also permits the different methods of printout, basic, PDF, or CSV. In some cases, CSV allows you to have, let's say, part limbs, but it's not a total automatic. It has to be, let's say, set up for that particular operation. My last slide here is I'd like to bring your attention to the fact that while we talked a little bit about particle size analysis utilizing the micro airjet sieve, we are going to be introducing the next generation micro airjet sieve here within the next couple of months. What's nice about it, what's enhanced about it, because the current model has some limitations, but it will enable you to be FDA CFR 21 Part 11 compliant. It will have the ability to have registries, so you will be able to conform in that particular field to the requirements of the FDA. The next is the earlier model had compatibility with limited balances and printers. That compatibility issue has pretty much gone away. The major names in the various balances will be compatible with the MAJS X2, next generation. And in addition to that, the drivers for the various printers enabling the printer will all be available, and you will be able to adapt it to any printer. One of the features that I like is the fact that the software can be modified to display any of 12 languages that are embedded in the software from the software's inception. However, keep in the back of your mind, if you have a language that's not embedded, which we go through the various English, Spanish, French, Dutch, German, Chinese, Japanese, Korean. If you have another language, we need to be made aware of that, and we will attempt to incorporate that into the software. Additionally, the vacuum pressure earlier model was limited to inch water vacuum pressure. We'll now have the ability to do Pascal, inch mercury, millimeters mercury. So you will not be limited to just identifying what your inch water value is. And not lastly, but one of the major highlights of this particular instrument is the fact that you will now be able to produce a 5 analysis overlay. So you can actually identify if you're going through a milling process. Well, this is my control sample. There's my particle size for the control sample. Now we have our feed sample. Then we have a sample analysis that was performed after the initial processing or after some parameters have changed in the processing or the milling process. You can compare up to 5 different analyses, and that'll give you a much broader and more information all from the single apparatus. All right, one thing that I would like to say, that is, if I have not contacted, or if I have not, let's say, addressed any of your particular concerns, what we'd like to do is offer the fact that please contact us at our web address and or our email, which is help@hmps.hosokawa.com. We'll be able to assist you. If you wish to contact me, my direct dial number is publicized right there on the screen. So I would like to thank you for your attention, your patience, and I look forward to potentially having a conversation or communicating with you via email. Thank you, and bye for now.